Greetings, my name is Ahmed Tayel, corresponding author and presenter of the paper accepted at the VTC 2021 Spring Conference. The paper title is Spectrum Access Management of Multi-Class Secondary Users in Hybrid Cognitive Radio Networks. First, an introduction to the point of research is presented, followed by a small background about related work in literature. The proposed system model is then presented, followed by simulation results. Finally, conclusion remarks and expected future work are presented. We consider a cognitive radio network with multiple secondary users and a single primary user. Additionally, the secondary users have a single receiver. The secondary users might have different quality of service requirements. For example, some users are text messaging, others are in need for an audio or video call. The secondary users can access the primary user's channel in interweave mode and utilize the spectrum gaps when the primary user is not transmitting. Or they can transmit simultaneously with the primary user in underlay mode. In this case, the transmission power is reduced in order not to cause harmful interference to the primary user. We target a hybrid interweave underlay transmission mode. Interweave mode is used when the channel is sensed free of primary user's activity, and underlay mode is used when the channel is sensed busy. Based on the previous discussion, some key features are considered in our model: the interweave and underlay transmission modes, existence of multi-secondary users, and if these secondary users are classified or not. Only the working 5 and 6 considered all features. We will call them Shaquille and Shao. In Shaquille and Shao, only 2 classes are considered. Their classification strategy is not flexible. Secondary user classes can only have certain throughput levels. In general, the high priority class has exclusive access to the channel resources. In more details, for the system under investigation, in Shaquille, the high priority class can access the channel using the hybrid mode, while the low priority class can only use the underlay mode. In Shao, more transmission opportunities are permitted to the lower priority class by limiting the high priority channel access to interweave. The proposed work on the other side can accommodate for any number of secondary user classes. Moreover, the proposed classification strategy is flexible to assign tunable throughput levels to the secondary user classes. The basic idea is realized by using the TDMA scheme. In each TDMA cycle, each class of secondary user is assigned a number of time slots according to his quality of service requirements. Assuming class I secondary user is assigned the set of time slots gamma I, and the current slot number is CT. First, the secondary user checks if he is allowed to transmit in the current time slot or not. If not, he would stay idle, update the counter state, and check again in the next time slot. If the secondary user is allowed to transmit, he will initiate channel sensing and check if the channel is idle or not. If the channel is busy, he will transmit in underlay mode, update the counter, and repeat the procedure for the next time slot. However, if the channel is free, the secondary user will transmit in interweave mode, then update the counter and repeat the procedure in the next time slot. Assuming perfect channel sensing with block fading and controlled underlay power, closed form expressions are derived assuming general mini-channel gain and general energy quantization steps. The closed form expressions are for the transmitted energy in underlay mode, the data outage probabilities in underlay and interweave modes. The simulation setting is presented in the table. In our model, the interference to the primary user receiver is considered. Additionally, the discrete energy levels can take any value. For simulation purposes, the quantization level is set to 1. Finally, the number of classes is set to 2. For comparison with related models, However, our analysis is valid for any number of second user classes. In this figure, the effect of the TDMA cycle length NC on the channel and the class throughput is investigated. For the second user time slot assignment, class 1 second user is assigned all time slots except for the last time slot, which is assigned to class 2 second user. Unlike Shakil and Shao, our proposed model shows the tunable performance with the change of NC. As NC increases, more time slots are granted to class 1 second user, while class 2 second user has only one time slot. Consequently, throughput of class 1 second user increases, while throughput of class 2 second user decreases. Channel throughput enhancement is 4.7% relative to Shakil and Shao. This enhancement increases as resources are distributed evenly among more users. This way, bad channel conditions are less probable to last for a long time from one transmission slot to another with different second users. In Shakil and Shao, most of the resources are granted for the high priority class with only 2 second user classes, which makes their system more affected by the channel conditions. In the remaining results, NC is set to 15, class 1 second user is assigned the first 10 time slots, and the class 2 second user is assigned the last 5 time slots. This figure studies the effect of the interference threshold of the primary user receiver, IT, on the performance. As the allowable interference level at the primary user receiver increases, the channel throughput increases. In this case, the underlay mode is allowed to transmit with higher power levels, and underlay mode is adopted in all models for at least one class. The idea of granting the resources more evenly among the users to achieve higher channel throughput is clear in this figure. Our model grants the lower classes more resources, followed by Chao, then Shakil, which is reflected on the total channel throughput. This figure studies the effect of the mean channel gains on the performance. In particular, the effect of the interference mean channel gains are investigated. The interference from the second user transmitter on the primary user receiver, and the interference from the primary user transmitter on the second user receiver. Maximum performance is achieved in all models at the lowest values for the interference channel gains. This way, the primary user transmission has negligible interference on the primary user receiver, and the second user can transmit with high power in underlay mode without interfering with the primary user receiver. Again, for the appropriate resource allocation among the second users, our model scores the highest throughput, followed by Chao, then Shakil. In this figure, the effect of changing the targeted channel throughput of the second user classes RC1 and RC2 on the performance is studied. Maximum throughput is achieved in all models at the lowest values for RC1 and RC2, where small target throughputs are easier to achieve. We can notice that the proposed strategy prevails for a large range of RC1 and RC2. When RC1 is low, in other words, in favor of the high priority class, Shakil prevails since he grants most of the channel resources to the high priority class. The proposed and the Chao models are more sensitive to RC2 change, since more chances are given to the low priority class. In conclusion, the proposed modified TDMA scheme provides solutions to several points. Point 1, it resolves the contention of the multiple second users to access the channel. Point 2, it provides the ability to schedule any number of second user classes. Point 3, it provides the flexibility to adjust the relative performance of the different second user classes according to their quality of service requirements. Simulation results illustrate these points compared to related work in literature. For future work, a couple of extensions of this work are currently under investigation. The fixed time slot assignment for the different second user classes can be extended to be dynamic. In this case, a resource allocation optimization problem will be initiated at the beginning of each TDMA cycle. More Practical issues could be considered. For example, imperfect channel sensing and its effect on the second user decision, energy harvesting capability, and limited battery capacity. This work is supported by the National Telecom Regulatory Authority (NETRA) of Egypt under the project entitled Security Reliability Trade-off in Spectrum Sharing Networks with Energy Harvesting. For any questions, you can contact me on the shown email. Thank you.